We're gonna go to our last story, which is a lot of times like do from really, really small now to like really
now
big
we're getting really big.
Now we're getting really big in space. California again. California forever goodbye. Headline: Brightest fast radio burst ever detected could help solve an enduring cosmic mystery. I love how people with headlines make it so unclear what you're talking about. Summary: researchers at University of California, Santa Cruz, we're going to Northern California, use newly developed CHIME outrigger telescopes and deep space imaging to challenge long-held assumptions about what causes these mysterious cosmic signals. I think we talked about one of these, if I'm not misremembering, the WOW signal was one of these like radio bursts.
It was a radio burst, right?
That we initially saw, and everyone freaked out and was like, aliens.
Yeah, it could have been. And that's not we haven't characterized that as a fast radio burst.
Fair.
Because we don't really know what the hell that was.
That's fair. That's still kind of like, what was that?
Yeah, what was that?
Fair. No, that's fair. That's fair. But it seems like we're now using, again, some of the tools we have. Also, this was in the Astrophysical Journal letters.
Yes.
In terms of the publication, CNN has covered this. UCSC also covered it in their own blog.
Yeah. It's a collaboration between UCSC, some Canadian institutions, Northwestern. It was a pretty big collaboration.
And because we need it. Okay, so what I don't like. What are because I mischaracterized. What is like this fast radio burst idea? What did they do?
Yeah.
Why like how are they? Why is detecting a bright one relevant?
Yeah, this one's incredibly bright. Okay. This thing within a fraction of a second output as much energy as the sun does for like 4 days. Okay. But this isn't even the brightest. Okay. This is the brightest we've had because it's the closest one to us. But fast radio burst, the first one was ever discovered in 2007. It was called a Lorimer Burst. It was actually taken from archival data from the Parkes Observatory, which is a giant 64-meter radio telescope in Australia. It's been called the greatest scientific instrument that Australia has ever produced.
Okay.
The greatest scientific instrument that Australia has ever produced.
Okay.
And it's the same dish actually was used during the Apollo 11 broadcast to like broadcast to the TVs around the world because NASA had like a thing at Goldstone that they were using, but this one was way bigger and the TV signal that they were getting from this one was just better than the rest, and so the NASA just used it for the whole 2.5 hours. Which is kind of cool.
Which is why the Five Eyes Ally, structure is helpful.
Australia, they got our back when we need it. So, they were on the right side. They were facing the moon, so that was nice.
Yep.
So this burst was discovered by Duncan Lorimer from West Virginia University. Basically, what he did was he assigned an undergrad to look at archival data from the Parkes Observatory. Okay. And the Parkes Observatory at the time had just released a bunch of data. It was a radio telescope that was just beaming up. And this undergrad would come in every week, and despite all of his classes and stuff, he would look at a bunch of data by hand and try to characterize it, and then try to find something interesting. And he found something very interesting. There was a brief millisecond duration, 5 milliseconds, but it was ridiculously bright. On top of that, it was not only bright, it had this very good characterization called dispersion. Okay? Dispersion is the idea that when light moves through a medium, through stuff, different frequencies are going to propagate at different speeds. This is fundamentally why we get a rainbow. Okay? Violet light actually propagates at a slower speed in water than red light does. Okay? And because of that, when light goes into a water bubble, the violet light is going to bend differently than red light, and that's what's going to cause the rainbow to come out. Okay? And then it gets like sort of focused and we get a rainbow. But the prism is the same idea. When it goes through glass, violet light goes slower, and so it's going to bend differently. Dispersion is this idea that there's a frequency relation to how fast light moves through medium. And in interstellar background, right, in the interstellar medium of these ionized particles, right, where it's like atoms without electrons moving around freely, you're going to have that opposite effect. You're going to have slower light, so slower frequencies moving slower than the faster frequencies. Just has to do with the different physics that goes on between a glass and a plasma. But at the end of the day, what that means is if there's a transient burst of light, the faster stuff is going to arrive first, and the slower frequencies are going to arrive later. And that's what's called a dispersion measure. Okay? This thing that they discovered in the Parkes Observatory data, which is now called the Lorimer Burst, had this very specific dispersion measure, which showed that it was of extragalactic origin.
Okay.
There was so much dispersion that meant that there was a lot of stuff that it had to get through to actually create that delay between the fast and the slow. And then when they back calculated how bright this thing must have been to be that far away, they were like, oh, this thing was incredibly bright. This was back in 2007. Since then, we've discovered multiple. There's been some that we've discovered where for that brief millisecond duration, this fast radio burst was brighter than the entire galaxy that it came from.
Wow. Okay.
Okay?
Yeah.
So it's been quite an insane sort of last few decades of trying to find these fast radio bursts.
Right.
The problem is they're really short-lived.
Right.
Okay, 5 milliseconds.
Unlike 3i Atlas, which we're watching for months.
Yeah, which we know for months, and we can like coordinate this thing. You know, it's there and it's gone,
and it happens,
and it just so happens, right? So it's been kind of challenging to actually find them.
Right,
it's been kind of rare. Along came this detector called CHIME in Canada, which is the Let me just get the thing right because I don't want any Canadians to get mad at me. It's called the Canadian Hydrogen Intensity Mapping Experiment, CHIME. It's a massive radio telescope that doesn't look like most radio telescopes. So, you know, most radio telescopes, you've got a circular dish with a receiver and the light goes that way. This thing is a bunch of half pipes that are just laid out on the ground.
Oh, interesting.
Giant half pipes, okay, 100 meters that are laid out on the ground, 4 of them in a valley in British Columbia, as south as you can possibly get, because what they're using the Earth's rotation to basically scan the sky in this radio frequency. Yep. And, you know, Canada's pretty far north, so they want to get as south as possible, so it's like right across the border from America. And it's this giant thing, and it's made such that it's really sensitive. It's got all these capabilities for as soon as a signal comes in. It's kind of like the Vera Rubin in terms of they've got online capabilities to analyze the signal. Yep. And it's also got a really good giant field of view. So it's capturing a big part of the sky as it sort of goes around the Earth. And very recently, so CHIME has found thousands of fast radio bursts since 2018. Okay. It's found a bunch. This one is very, very nice because usually when CHIME finds fast radio bursts, it can't localize where it came from. Right. Because it's got this giant field of view, it just sees sort of a signal. Yes. And it's like, okay, I saw a fast radio burst. Yes. Don't know where it came from. So what they did was, in collaboration with America, they made more CHIME stations. There's one in California, there's one in West Virginia, there's one also in Canada. And now what you can do is triangulate.
My favorite.
Right? And what you can do is, if you get a fast radio burst, you're going to get that signal all over the place. Yes. And you can triangulate where it came from and actually resolve what part of the sky it came from.
Because you have multiple receiving points at different places on the planet.
Exactly.
And so the angle
is going to be different, and the timing is going to be different. And you can back calculate and see where it came from. Yep. And what they could do is they could resolve it to a really tiny area in the sky, right around the Big Dipper. The equivalent would be to resolve a quarter from 100 kilometers away. Okay. Very tiny spot, right? And that gives you the advantage because now if you know that it came from there, you've got all these other telescopes on standby that can point right there, right? That's exactly what they did. They got the James Webb. Yes. They called in the big guns.
Yeah, they called in the big guns.
They called in the big guns because this one was really bright. Okay. In terms of, this is the brightest fast radio burst that we've ever seen because of its proximity to Earth. Not in terms of intrinsic brightness, but because of its proximity to Earth, now it's really exciting, right? Because now we can point optical telescopes to it and we can actually see what part of this galaxy that it came from. It came from NGC 4141, which is this barred spiral galaxy. And what it does is, and you can localize the neighborhood of that galaxy. Not just that it came from that galaxy, but it came from this corner of the galaxy. Okay? And now you can point James Webb Space Telescope to it, and James Webb was pointed to it. It found a faint signal in the infrared. Okay? Right around that same spot. And that probably came from some massive stars, like a red giant or something like that. Now, doesn't quite fit that a red giant or a big star would create a fast radio burst. Okay? Because those things are like slow.
Right.
They're not 5 millisecond timescales.
Right.
5 millisecond timescales are the stuff of black holes, neutron stars. They revolve really fast, you know?
Yes.
So there's timescales that sort of correspond to astronomical objects.
Yes.
Right? And so now it leaves us with a conundrum. It's like, where did this thing come from? Mm-hmm. There's hypotheses. There's not good data because, again, this is the first time. I mean, CHIME and the CHIME outrigger stations only came online like this year.
Okay.
So this is the first thing that it's found. Mm-hmm. And it's very exciting because it's kind of a proof of concept that it's like looking and it can find it, and then we can go off with James Webb Space Telescope, with Keck, with Gemini, and point it at that and then actually see a follow-up observation, right? Mm-hmm. So we still don't know really where this thing came from. What we do know, which is very interesting, is this might be a one-off. Most of the fast radio bursts that we've seen, they seem to be repeating fast radio bursts, right? Where they've got this rhythmic sort of structure. The rhythm can be very long. It can be from days to months to years. But they've got this rhythmic thing where it's like, okay, you've got one really bright one, but then every once in a while, the same source should put off like sort of smaller bursts.
Which I think is why it matters that we have this multi-sensor data confirmation, multi-sensor collaboration to be able to isolate a smaller point in the sky, because if we do find these rhythmic sources, we can point these other tools there for longer periods of time.
Exactly.
To try to potentially catch what is this. It reminds me of the transients conversation we had the other day, where it's like there's this rhythmic pattern of the planet, the exoplanet going in front of a star.
Yeah.
And so you have to monitor it for certain periods of time to understand that it's not a one-off.
It's not a one-off, yeah.
And so what's interesting here is like what we're potentially seeing with this specific really, really bright one may have been a one-off.
It may have been I mean, we think it's a one-off because CHIME was going around that same spot in the sky for the past like 7 years. It's had hundreds of hours in that region of the sky.
It's the only one.
So we've only seen it once, right? And it would have found even smaller radio bursts, but it hasn't. And so it's like, what could be this one-off thing? It could be they're thinking it might be a magnetar, which is this. A magnetar is
not a Pokemon.
No, it sounds like one though. A magnetar is sort of a newly born neutron star that's highly magnetized. So it's got really powerful magnetic fields, and it's in a sort of new stellar neighborhood that has magnetic material around it. So it can create these fast radio bursts by sort of, maybe it's like accumulating material and then it blows up or something. Maybe it's accumulating material from the red giants that the James Webb Space Telescope saw. The James Webb saw some signal. They just don't know. It's like not good enough,
it's not good
right?
enough.
And because it's transient, it only happened for a little bit, and then it's gone. It's not like a star that I can just keep looking at and getting data, right? It could be a magnetar. It could also be a colliding neutron star. But if it was colliding, sort of revolving colliding neutron stars, we would have seen LIGO.
Yeah.
We would have seen gravitational waves, which we haven't in the hours preceding or since. So maybe the collision is going to happen later, and this is like maybe they're getting close and doing some weird dance, and then that like released a giant fast radio burst. But it's a new scale of astronomy, right? Where before we had like only a few stations that were relying on the Earth's rotation to like maybe catch something, right? And now we've got a dedicated sort of instrument that is doing it on the northern hemisphere. You can imagine we can create a global celestial radio instrument that now does this. Actually, the VLA also took a look at it because now that we can locate it here, the VLA took a look at it for like several days afterwards, trying to see if there's going to be a repeat. Didn't see one.
So this VLA does being the Very Large Array.
Yes, the Very Large Array in New Mexico, which is a giant interferometer of a bunch of radio dishes on train tracks.
For those who I think the movie was
Contact
with Jodie Foster.
Was written by Carl Sagan.
Written by Carl Sagan was at the Very Large Array. Class with, but again, this goes back to, I'm glad the outriggers were able to get out before funding got cut. This is why things like CHIME, the Vera Rubin, which have this very specific use case of sky surveys, that are not that are just saying we're just going to get this this data set.
Because we don't know where to look.
We don't know where to look.
We're just looking everywhere.
So we're going to create this map.
Yeah.
And then that'll help us know where to look.
Yeah.
And then everyone can write their proposals to then use these specific other tools to then look much more deeply.
Yeah. And I mean, fast radio bursts are only 20 years old. You know, in terms of the grand scale of astronomy.
Right.
That's hundreds of years old science.
Yes.
Right? Like only 20 years ago we found the first one. And these things are so ridiculously bright. And it's like, what could possibly be making something that is as bright as a galaxy for a fraction of a second?
Right. Right.
You know?
Don't get the Dyson sphere people in on this. Be like, oh, obviously it's an alien civilization that's harnessed the power of a planet, and then when they recycle their generatron, it sends out this massive. I'm being facetious.
Yeah, we should have an episode about Freeman Dyson though. He's one of my favorite physicists.
Same.
He's one of my favorite physicists of all time.
I love Dyson.
Yeah.
Very clever.
Yeah.
Interesting.
Really
creative.
funny too.
Yeah.
Really funny guy.
Brightest fast radio burst ever detected.
Yeah.
Because of some of the tools that we have, this is such a new area. And we haven't figured it all out yet.
No.
There are really
there are mysteries out there in the universe.
And we are doing good work to try to narrow the path towards discovery on some of these things.
Yeah. And it's like, you know, when the Vera Rubin, I was listening to the press conference for the Vera Rubin the other day, and they were talking about they used Donald Rumsfeld's unknown unknowns.
Classic.
But it actually made sense here because you know there are the known unknowns, which is like what is causing the expansion of the universe, what is dark energy, what is dark matter, what are these fast radio bursts.
Yes, we know that they're there, but they're unknown in
what they are.
Right,
and then he said, what I'm really excited about with the Vera Rubin is the unknown unknowns. Because before 2007, fast radio bursts were an unknown, right?
Yeah.
People couldn't even imagine that something like this would exist.
Right.
Where in 5 milliseconds, it dumps like a ridiculous amount of energy.
Yes.
You know, that time scale for that amount of energy is insane.
And who knows what number of unknown unknowns
the Vera Rubin is going to find.
As we have these better tools.
Yeah. And what the CHIME is going to find too. Maybe it'll find like super fast radio bursts, you know, that are like at the microsecond level.
Right.
You never know.
You never know.